So if we're using the definition here, we continue to apply the limit throughout until we get this simplified form we can apply the limit to. And we begin by figuring out what f of x plus h is. We take x plus h, insert in the place of x in the original function, get the square root of 1 minus, okay, it's 1 minus 5 times x plus h if we're replacing x with x plus h. So since I'm multiplying this minus 5 to that, I'm going to say minus 5x minus 5h. In other words, I'm distributing that negative 5 through. Not that you have to do that at that step, but at some point you'll want to. Okay, we are subtracting. Now we have to insert the original function. And that is all over h. Okay, so with these limits, as we apply a limit to a rational function that has a bunch of roots in it, the little trick we've been using is conjugates to help us get rid of those roots. So I'm going to use the conjugate here of the numerator expression. So that conjugate would be square root of 1 minus 5x minus 5h plus square root of 1 minus 5x. I multiply that to the top, I multiply that to the bottom. Then the rest of the trick that we use as we multiply by conjugates is we recall we only multiply the conjugates. So the denominator here will remain as h times this square root of 1 minus 5x minus 5h plus square root of 1 minus 5x. If we multiply out the conjugate expressions in the numerator, multiplying the first terms here, roots cancel, and you're left with 1 minus 5x minus 5h. We multiply the last terms, understanding that it's a negative times a positive, so it's minus whatever this quantity result is. So that quantity result, when we multiply these last terms, is going to be 1 minus 5x, because again, these roots are just canceling out. So having that minus applied to this quantity is significant because you do have to carry this minus through and change the signs on these terms, meaning if we combine like terms, the x's disappear, the 1's disappear, and we're left with a negative 5h, meaning this h in this term can cancel with this h down here. And if we write our simplified form now for what we're applying the limit to, we'll have a negative 5 in the numerator over this root expression. At which point, what we're applying the limit to, this function is completely simplified. We can insert 0 in the place of h, meaning any of these h terms are going to 0. So in the end, we'll have negative 5 over the square root of 1 minus 5x plus the square root of 1 minus 5x, meaning you've got two of the same root expressions, right? So really, your answer would be negative 5 over 2 square root of 1 minus 5x. There's your derivative using the definition. All right, so if we're using the definition on this one, again, we apply the limit throughout until we got a completely simplified function we can apply the limit to. We start with our substitution. We replace f of x plus h. We replace that with, well, whatever we get back when we take x plus h and plug back into the original function for all the x's that we see. So I'm going to plug in x plus h up here. I'm going to have 3 times that quantity of x plus h. That means I'm going to have 3x plus 3h. That's over. I replace this x with x plus h, so it's x plus h plus 6. We are subtracting. Now I have to substitute in for f of x. If I substitute in for f of x, I've got 3x over x plus 6, the original function. And that is all over h. So we got these fractions within a fraction, meaning we got to clear those fractions out. So what we're going to do here is we're going to take these denominators, and in theory we're going to multiply numerator and denominator by that product of denominators. If we do that, what ends up happening? Got our limit down here still applied because we haven't simplified the function. Let me start with the denominator portion here. You've got an h on the bottom already. And like I said, in theory, we're multiplying top and bottom here by these two denominators. So I'd have x plus h plus 6 down here and x plus 6 down here. Now, because I'm multiplying both the top and the bottom by these two denominators, that will allow me to cancel these fractions out and to adjust for what would be left. This is where we use that little cross multiplication trick. I'm going to take this 3x plus h, or I'm sorry, 3h rather. Take that quantity, multiply to x plus 6, and then subtract. We've got 3x here, multiplied at its respective diagonal here, which is x plus h plus 6. If I use that little cross multiplication trick, it allows me to cancel out the fractions. Now this is where we're at, and we got a lot of distributing to do. So if I do my distribution, got some foiling I can do right here. If I FOIL, I've got 3x times x, so 3x squared. Outside terms would be 3x and 6, so that'd be 18x. Inside would be 3h and x, so 3hx. And last would be 3h times 6, so 18h. Now if I distribute this negative 3x through, I've got negative 3x squared when I multiply to x. I've got negative 3xh or hx when I multiply to h. And I've got negative 3x times 6, so that's going to be negative 18x. Got my distribution done. In the denominator, I leave all this alone. Want to leave it factored because it makes things easier to cancel out here in just a moment. All right, let's see what we can get rid of. We've got some x squared terms that disappear. We've got some hx terms that disappear. We've got some x terms that disappear. And all we are left with is an 18h. Since we left the denominator in a factored form, this h here cancels with this h here, meaning our simplified form, we are still applying our limit to at this point, leaves us with an 18 on top and a quantity of x plus h plus 6 times a quantity of x plus 6 on the bottom. Finally ready to apply 0 to all of the h terms. We just have the one h term right here, so that goes to 0, meaning you got a quantity of x plus 6. So my final answer now, limit's been applied, got 18 over. If this is x plus 6 and this is x plus 6, you've got two of those that are being multiplied together. You could say x plus 6 as a quantity squared. All right, Alright, so directions here on 2 through 11. We're just finding the first derivative. We don't have to use definition. And it says we don't have to simplify. Okay, now, speaking of simplifying, there is something I would do with this initial function to tweak it to make it easier to take the derivative. If I notice any x expressions down the denominator, like I do over here, I would take that x with its respective power and I would bump that up. So I'm going to take this guy right here. Understanding this power of 1 is only applied to the x, not to the 2 also. I'm going to rewrite this as 5 halves, because 2 has to stay on the bottom. X, if I bring this up, it'd be to the negative first power. So I'm going to tweak that there. By tweaking that, we've got 4 terms where I can simply apply a power rule to those 4 terms to take the derivative. So now I'm ready to take the derivative. I note that I'm doing that by writing f prime of x. Going through using my power rule, take 5, multiply to 12, get 60, subtract 1 from the power, the x to the 4th. Here, take negative 2, bring down to negative 4, multiply. That makes that positive 8. It's going to be positive 8x. New power, because I'm subtracting 1, it's going to be negative 3. I've adjusted this term here, so I bring down negative 1. If I multiply negative 1 to 5 halves, I get negative 5 halves x. Subtract 1 away from the power, get negative 2. And then the 136, that's a constant, so derivative of a constant is 0. There is your first derivative. You're done. All right, so taking the derivative on this one, you've got f prime of x equals anything sitting in front of the trig stuff, that's being multiplied to the trig stuff. But since this is just a numerical value, this 12 comes along for the ride. Okay, now we have to use what we know about our chain rule with regards to trig functions. So what we know about our chain rule with regards to trig functions is we start with this tangent concept and we think about the derivative as it relates to tangent. So as it relates to tangent, that would be secant squared. So I write secant squared. And then this x minus 9, which followed the original trig function, that stays put. That follows this derivative for tangent. But now I have to consider the derivative of x minus 9 and tack that on. That completes the chain. So if I tack that on here, derivative would just be 1, because this is a 1x, x would drop out, 9 goes to 0. So in an unsimplified form, that's it for your derivative. Next problem is a quotient. So we've got f of x equals x cubed plus 3. That's all over 8x to the 4th minus 1. So again, just a quotient. If I take this derivative, I start with the derivative of the numerator. So derivative of x cubed plus 3. Just going to be 3x squared, because that 3 goes to 0. I'm multiplying that to the original denominator. We're subtracting the numerator. Be careful how you're using parentheses here, right? If you got multiple terms, we're multiplying a lot of stuff out. You do need parentheses around those multiple term quantities. To this, we're multiplying on the derivative of the denominator. So derivative of the denominator would be, bring down the 4, multiply to 8, so 32. X, subtract 1 away from the power, cube. Minus 1 goes to 0. Okay, that makes up the numerator portion of your answer. This would all be over, though, your original denominator, all of that squared. So again, unsimplified form, which is what you can leave this in, that's your answer. All right, so we see all the roots. We know if we got all these roots, we're going to take a derivative. We've got to raise these roots. So if we raise all the roots, underneath the cube root, you've got the cosine of, all right, a fourth root applied to 7x, so that's going to be 7x raised to the fourth. All of this is raised to the 1/3 power. So adjust for your roots accordingly. Now, taking the first derivative, well, let's see. We start with the outermost power applied, which is 1/3. We bring the 1/3 down. I'm going to kind of check some things off here as I go, right? I'm taking care of that right now. That means everything inside here stays the same. And since I'm only adjusting for that outermost power, I'm subtracting 1 away from 1/3, I'm getting negative 2/3 back. So step 1 is complete. Now let's move to the inside here. If I'm taking the derivative of the inside here and tacking on what I get, I see a trig function. I see a cosine. So for cosine, I'm writing negative sign. And that takes care of that piece. But that piece was applied to the 7x to the 1/4. So that has to follow. So I'm checking things off as I go. I come back up here, I look to see what's left. Well, what's left to take the derivative of, I'm going to tack on here. And I see that a power is applied overall to this. So this power of 1/4, I'm going to bring that down. I'm only acknowledging this power right now, so this 7x stays put. And adjusting for this power coming down, I'm subtracting 1 away, so I've got a negative 3/4 left. I come back up here one last time and look to see if there's anything left to play with. There's still a 7x. So this 7x, if I take the derivative of that, I get 7 and tack that on. There's nothing left to play with up here because I've checked everything off. I must be done. There's my first derivative in an unsimplified form. All right, so 7 being like 6, we've got a product. We've got this piece multiplied to this piece. So following the product rule again, f prime of x is going to equal derivative of the first piece. So that's going to be 6x squared would be 12x the first. Got plus x here, so that's a 1x. We'll say plus 1 as the x drops out. The 9 goes to 0. This entire quantity here represents the derivative for the first part. Continuing with the product rule, we tack on the second part as is. We add the first part as is times the derivative of the second. So understanding this second piece is x to the 6th minus 8th raised to the 1/4 power. I've got to bring down a 1/4. The x to the 6th minus 8 stays the same. Brought down a 1/4, so you're subtracting 1 from 1/4. You're getting negative 3/4. And we are tacking onto that the derivative of the inside, which is 6x to the 5th, because 8 goes to 0. There's your first derivative on 7. All right, so find an f prime of x on this one. Well, let's start with the first part of this expression. You've got x plus 1 times sine of x squared. We've got a product rule that we have to apply right there. So using the product rule, take the derivative of x plus 1 first. That derivative is just 1, right? So it's 1 times the second part as is plus first part of the product, x plus 1, written as is, times the derivative for that sine of x squared. So, taking a derivative with a trig function, we take the derivative with respect to sine first. We understand cosine is connected there to sine. We write what follows originally, and that was x squared. And then we tack on the derivative for that x squared, 2x. Everything in red here represents the derivative for this product. But we are subtracting another product where I have x times the cosine of x. So take your derivative of x to start, giving you 1. The second part of the product stays the same because of the product rule, plus first part of the product x staying the same, times, well, the derivative of the cosine of x. Derivative of the cosine of x is just negative sine of x. That completes your derivative. Yeah, before we move on to 9 here, I noticed on 8 we were subtracting, right? So I've been emphasizing as we take these derivatives, if you got multiple terms, you got to make sure that you're trapping them in parentheses, right? So in this case, I'm subtracting the derivative of this. So this is that entire derivative, which has multiple terms because of the addition. I do need some form of parentheses or brackets around that to show that I understand the subtractions applied. You can follow my own advice. But I caught it, and I corrected it before you guys did, so there. I win. All right, moving on to the derivative here for 9. Another busy problem. But I've got basically 3 kind of terms here to acknowledge. And I just got to decide what's the best kind of rule and approach to use for each of those terms. So you start with the cosine of x cubed. Got a trig function, right? Got something that follows the trig function that's part of that trig function. That means I start with cosine, I take its derivative, which is negative sine. I write what follows, and then take the derivative of what follows. So derivative of x cubed is 3x squared. That takes care of this piece. We're going to add on derivative for this part. Now, derivative for this part is that same product that we saw back here on number 8. Back here on number 8, we had it right here, which gave us this, right? And we're adding on, so I noted the mistake I made there on number 8, talking about the parentheses. So throwing parentheses in here would be nice, but since we're adding it on, I'll be honest with you, it doesn't matter. But if I group this, just to distinguish, I take the derivative of x first, which is 1, times second piece, cosine of x, plus first piece x, times derivative of the cosine of x, which is negative sine of x. So all of that is the derivative for this part. And we did have to use a product rule. All right, finally, we are subtracting our derivative with regards to this final piece. So we got a trig function again. It's applied to 2x to the fifth. So start with derivative for sine, which is going to be cosine. Write what follows being 2x to the fifth, and then tack on the derivative of that 2x to the fifth, being 10x to the fourth. There's your derivative for number 9.